We already have some review on the cold flow structures for a jet, a gaseous jet. And then now we start to learn the diffusion frame possibly stabilized in this jet flow. And these figures tell you an experimental results. And by using methane as a fuel, and those methane go through the small tube and ejecting out of the burner and to the stagnant environment. Okay, and we try to increase the injection velocity and to observe the appearance of the jet diffusion frame. Now, this plot tell you we have some measurement for the frame length. Okay, now we start to look at the variation of the combustion characteristic for such a fuel injecting out purely to the oxygen environment. Actually, the tube inside the tube are pure methane, and they are separate with the oxygen from the surrounding. That means that when you ignite it, you will generate the so-called diffusion flame. When you look at the region for the small injection velocity, that means that we are looking at the laminar diffusion flame. When you look at the variation of the flame characteristic for a given laminar diffusion flame by increasing the injection velocity, three important characteristics need to be mentioned here. The first one, the change of the flame length by increasing the injection velocity. Actually, from our theoretical prediction, simple formulation, you will find out actually flame length is proportion to the injection velocity. That means that when you increase the injection velocity of fuel, then your flame length will increase almost linearly. Actually, those prediction is successful by the theoretical analysis, but in experimental observation, it seems very nicely fit with the theoretical prediction because the flame length is almost increased linearly with the injection velocity, but slightly higher for compare with the predicted value, and look like the parabotic shape. And this discrepancy between the experimental result and the theory prediction basically caused by the natural convection. Okay, in the theoretical analysis, we ignore the influence coming from the gravity, but in real experiments, since we have some buoyancy effect acting on the fuel has a high temperature, right? Then those kinds of buoyancy effect will push your flame a little bit higher than the predicted value. And but you can see the flame height actually is continuously increased, monotonically increased with the injection velocity. This is the first observation. The second observation is you can see the flame color. Basically, they are yellow. Okay, they are yellow. This is a typical appearance for diffusion flame, as we explained earlier, for the candle flame, because the inside of your diffusion flame accumulates a lot of carbon particles in the high temperature region. They will they will release the yellow emissions, and you can see the light is uh, quite clear to tell you they in the inside of the diffusion flame they have a certain amount of carbon particles that is a sooty flame. But however, you can see the button of the jet diffusion flame always show you is not clear to observe because this is the blue color in on the loop of the jet diffusion flame. In this region, later on I will explain to you because we have more oxygen can be diffused into this region closer to the exit plane or burner. Then they have a sufficient oxygen to burn out the carbon particles, then the flame color change to the remains the blue color. Additionally, those kinds of unburned carbon will move to the downstream side to have some collision each others to create a large size of a carbon particle. This is another effect. Therefore, in the downstream sites, we have a more strong yellow color. The intensity of the carbon particle radiations become very strong. This is the second observation you can see. The third observation is you can see the French surface are quite smooth, even they are wrinkled. Okay, this kinds of wrinkle is very similar to our previous discussion on premise frame. When the premise frame experience the ADs coming from the air, those large AD will give you the influence on the French surface become curved, and we call this as a wrinkling. But for laminar jet diffusion frame, actually you can see those kinds of curvature on the French surface is quite obvious, because this is obviously this is caused by the influence of the large AD. Okay, but in this region you can see frame length increase, and then they have some kinds of large scale fluctuation, and color become it's a totally is a yellowish, except the base of your diffusion frame. This is the first part from, for example, maybe in this case from the 0 centimeter per second up to the 100. I'm sorry, it's a 1400, maybe 1400 centimeter per second, and corresponding to the those kinds of characteristics corresponding to those for the laminar diffusion frames. Now we go to the next region. We increase the injection velocity higher than 1400. Then you can see that there is some fluctuation occurs on the diffusion frame surface, but starting from the tip. Okay, you understand there is that if you have a jet, when you go through the actual directions, the flow, the actual momentum will be reduced. When you go to the further downstream, actually the velocity become very small. And for this region with the smaller flow velocity, it is easier to be influenced by the fluctuation coming from the outside, which means when you have some disturbance in your surroundings, the first effect on your frame will start from the tip of your frame. Then you can see when the frame length reach to the highest point for this experiment, they can reach to the 60 centimeter height, but they start to have a strong fluctuation occur on the top, and this fluctuation will propagate from the top through the upstream side. You can see those fluctuations will move downward, continuously. Actually, this tell you they start to have some kinds of turbulent behavior occurs on the frame, but those kinds of behavior starting from the top of the diffusion frame and propagate, and those small scale fluctuations become more severe and propagate to the upstream side of your frame. And typically, you can see for many kinds of hydrocarbon fuel, they will show you there is the abrupt change occur. For example, here, when you reach to the around 2000 centimeter per second, you can see the frame has some abrupt change there, dip off. This is a typical features for the jet diffusion frame. When you increase your injection velocity to a certain value, actually your diffusion frame cannot be stabilized at the Bunsen at the burner exit, and the frame will dip off and stand at a certain distance away from the exit plane of the burner, just like this example. Okay, and this kinds of transition occurs later on. I will tell you why is the reason for this kinds of transition. But anyway, when you jump to a certain position, surprisingly, this is completely different with the premise frame. When you have a premise frame cannot stabilize at the burner axis, they move away from the exit plane burner, but they cannot find a position to stabilize it, then easily to be go away. So we say this is so-called the blow-off, right? The blow-off is one of the important combustion characteristics for premise frame. Why the premise frame cannot stabilize at a certain position in your flow? This is simply to understand that because the position of your premise frame is stabilized under the dynamic balance. Dynamic balance is as you need to find a place or position. The frame speed just balance and very stably with the supply velocity. But in reality, in the flow structures, for example, for one of the positions in your flow, you cannot have a very stable flow velocity at such positions, which means the flow velocity may change and they should have some fluctuation. That means the position is not the so-called stable position, it's a dynamic position, which means the premise frame it is very hard to stabilize a certain position without any support, then they should blow off. For example, if you have some stabilized strip or even a wall, then the premise frame may have a chance to stabilize that. But in the open flow, it is not possible. But surprisingly, for diffusion frame, they can be support at a certain position. Okay, here this is quite different. And there, if you continuous increase your injection velocity, something happen, you will find out there still have three important characteristics that you need to mention. The first one, the frame color has a big change from the yellow to the blue, okay, to the blue one. And you find out you try to count the frame length for the turbulent diffusion frame from transition region. If you increase the flow injection velocity higher than 2,000 centimeter per second, then you will find out the frame becomes a turbulent diffusion frame. Color change from the yellow to the blue. This is the first one you need to observe, to look at it. And the second one is the frame length. If you count the base of your frame up to the top of the frame length is almost the same, right? Do not change too much. Okay, this is a second observation. The third observation is now the frame basically they will experience that fluctuation without the wrinkling as we explained for the previous frame. In this sense, in the turbulent flow now you have too many small ADs. Those small diameter of ADs will give you the very strong fluctuation on the frame surface. You can see here, you cannot see, you do not see the curved frames, but instead a very strong fluctuation. These three features basically you can observe for the turbulent diffusion frame. And now, if you try to bring the laminar and the turbulent frame together, actually these two pictures to give you some typical frame structures, frame observations for the laminar and the turbulent diffusion frame. The left-hand side show you very smooth, nicely frame surface, right? But the right-hand side tell you there is some actually this turbulent diffusion frame corresponding to the influence coming from the low intensity turbulence. Okay, those low intensity turbulence, that means that you have a larger turbulent ADs, then they will give you some curvature or a wrinkling of your frame surface. Okay, and this is two pictures for you to have some understanding on the differences for the laminar and the turbulent diffusion frame. But if you increase the injection velocity very much, the frame structure should not be occur like the picture shown in the right hand side, because they will go through the blue frame with the very strong fluctuation. Okay, and here I want to mention for the laminar diffusion frame. Here we mention this frame is under the low speed, because for the those so-called laminar flow means the flow is sometimes they have a different layer motion. Okay, then we call this laminar. Is definitely the flow will follow the straight line continuously. Then it is very consistent, and they will show you a very smoothly frame surface. But for the high-speed flow, the flow has a certain amount of ADs, includes a small one or big one. those kinds of AD interactions will strongly influence on your friend's surface. Then the friend will experience a very strong fluctuations. And in our previous observation, you find out the friend lengths do not change too much for when you increase injection velocity of your flow. And typically, you can see continuous increase your injection velocity in this turbulent jet diffusion frame region. You figure out as you increase the injection velocities, okay, you can see starting from the dip off of your diffusion frame, and you will find out the frame length is almost remain constant, and the dip of length actually is slowly increase as we increase the injection velocity. But finally, you can see for a typical jet diffusion frame, usually you will have this kinds of results where you increase your injection velocity up to 4,200 centimeter per second. Then this frame will cannot be stabilized at certain point in your flow, then they will disappear. Okay, that means the flow of the frame will blow out of your jet flow, which means in this case you will experience too strong turbulent intensity. Then this frame cannot survive in at these positions. Okay, this is the so-called the blowout, which means that the instability for a given jet diffusion frame will be limited by two important characteristics. One is the frame dip off. The frame will sit at certain positions at your flow in your flow, and finally you will find out the frame cannot sustain the very high turbulent intensity. Then they will blow out from the frame. Then we give a short summary for premise frame. The stabilization of frame will be limited by the so-called the flashback and the blow off, right? If the frame speed is higher than the supply velocity, then frame will flash back into your fuel supply, the mixture supply part. And if your frame speed is smaller than the flow supply velocity, then the frame cannot stabilize at the burner exit. Then the premise frame will stabilize by this limit, flashback, and blow off limit. But for diffusion frame, actually they can stabilize on the port of your burner. Your injection velocity should be smaller injection velocity as for the dip off. Okay, in this region you can stabilize your frame at the port, but when you have a frame dip off, but you still have some chance to have a stabilization of your jet diffusion frame in certain positions, and still continuous burning, but there is a limit for defined as the blowout. When you have a velocity higher than the velocity required for blowout, then you will not have a diffusion frame. But in real application, actually, we do not suggest that we use the injection velocity in the range between the dip off and the blowout, because there is show you the certain the uncertainty for the stabilization of jet diffusion frame in your flow. It is not safe for operation, which means that you need to keep the flow velocity small enough to prevent the frame dip out from the base of your burner. Okay, now we try to explain how the motion of the frame from the port to a certain position in the flow then blow out away. And we try to go back a little bit, and let's look at the cold flow structure as I explained to you. And this is the potential cone, right? You are clearly understood. And here there is some ISO 9 for the ISO composition 9, ISO velocity 9, and also ISO thermal 9. You can refer to these curves. Okay, now the first one, we think about if you have a cold flow structures like this for jet flow. you can identify and you can estimate the positions of the different kinds of flame you may have. Okay. For the diffusion flame, you figure out this is a typical. I apply it. Yellow represent there is a sooty flame, right? I already explained the jet diffusion flame has the yellow color. Okay, but in the lower parts, closer to the burner exit plant, then the flame become is a blue. And this connection. This is a total appearance for a jet diffusion flame. And here I try to mention when you have a cold flow described by the ISO 9 analysis, and you will figure out if you try to ignite it to produce a so-called jet diffusion flame. Simply to think about, you just inject the fuel out to the oxygen environment, which means you have an air in outside. Then you try to expect where is the flame position. Definitely you will find out, because the flame position is determined by the balance of the diffusion strength between the fuel, inside fuel, with the outer oxygen, right? Then you will figure out the diffusion flame may sit in the very closer to the interface between the inner fuel and the outer oxygen, right? Then the flame position, you can expect they will sit certain at a certain position near the jet boundary, as I described earlier in our experiment for the opposed jet flow, right? You impinge the fuel and the oxygen together uh, to uh, uh, to meet together, and you ignite it. You will have a planar diffusion flame sit very closely, even just fit with the stagnation plane, because the stagnation plane is the boundary, is the interface to separate your upper flow and the lower flow, right? And in this sense, from our experiment observation, even here you can see the diffusion flame should sit very closer to the interface or to the jet boundary, but they should not have exactly, because this this zero value ISO 9 represent the jet boundary, but this is another the indication for the balance of the diffusion transport. For example, depends on the concentration of oxygen and the fuel you have for both sides. For example, for the fuel burned in the air, then you can see flame maybe sit very close to the jet boundary. But when you increase the oxygen concentration in your environment, which means you will increase the oxygen diffusion transport, right? You will enhance it. Then the oxygen has a strong intensity to diffuse more oxygen into your jet. Then this flame will shift a little bit closer to the center portion. Okay, move to the center portion. Okay, this is the tell you the first estimation. You will expect the flame very close to the boundary of your jet, the jet boundary. But secondary, you need to think about the diffusion strength, a balance between the fuel and the oxygen. Okay. Now, this is an idea to estimate the position of the diffusion flame. But the next one, when you move to the right-hand side, typically this is the identification for determining the position of the premise flame, right? As I explained earlier, when you have a rich premise flame, then you will have a flame sit very closer to the potential cone, or even into the potential cone. It's a small flame, blue flame. But for the rich one, for the rich premise flame, you have a certain fuel depth after premix burning, and those kinds of fuel depth in the downstream of your premise flame. Those fuel still can have a chance to burn with the oxygen in the surrounding air, right? Then you will produce another so-called the diffusion flame. But this diffusion usually we use the blue to represent, since the rich premise flame, you already burn out a certain amount of fuel. You just have small amount of fuel left in the downstream side. They do not have a chance to have a very large amount of carbon particle exist in downstream. Therefore, the blue flame is possibly exists instead of the original yellow flame for regular diffusion flame. And as you have a double flame exist, actually these two flames support each other. As you remember, for our premise flame experiment, you can have a 20% or 80%, 18% methane flame stabilized in the Bunsen burner, right? 18%, 20% actually is exceed the rich limit of methane flame. The rich limit for methane flame is around 15, right? 15 means that if the mixing ratio higher than 15, you cannot ignite it because the flame cannot survive. Okay, but for the jet flame, surprisingly, you can have a rich premise flame under 18% and 20%. Why? When you have a 80%, 18% and 20%, and you burn this rich premise flame in the outer air environment, which means you will have additional secondary flame. The diffusion flame exists in downstream of the premise flame. And this diffusion flame will support, because they will release heat. Those heat will support this rich premise flame. Originally should not survive, but now survive because the support coming from the diffusion flame. Okay, and you can see clearly there is the rich premise flame under 18%, and in this case the diffusion flame supported it. Okay, now in this case we will call this rich premise flame is under superheating. Superheating, that means that in downstream they have additional energy to support your flame survive.